Well, good morning, everybody. Good morning, everybody. It's definitely a pleasure to be here. I've been giving presentations on the Utica Shale and some of the environmental things that go along with it for quite a while now, and it seems like the stages just keep getting bigger and bigger. I want to give you a little bit of background on where I come from, and why I think this is a very important development for our region. First of all, my wife and I, we have a nice little 20-acre slice of paradise down in Columbiana County. We've got a green construction home. We have a constructed wetland to take care of the agricultural runoff. We have a forestry management program, planting nut trees, and we just love living out in the country. About 15, 16 months ago, I got wind of Utica Shale development probably coming to Ohio. And that was about the same time I took over chairing the Department of Geological and Environmental Sciences. And I thought when I heard about this, there's a great way for our department, geology on one foot, environmental sciences on the other, to be involved in this in a very constructive way. And so what I'd like to present to you today is some of the basics of what goes on with oil and gas production, hydraulic fracturing, and some of the environmental concerns we need to be looking out for, particularly when it comes to our water resources. Ohio is not new to oil and gas development by any stretch of the imagination. Oil and gas development started in the late 1800s, 1860, and it's been growing ever since. We've gone through a number of stages of development. The map that you're looking at actually shows the distribution of oil and gas fields in the state of Ohio. And as you can see, eastern Ohio is got quite a bit of oil and gas fields. The red areas pretty much are gas. The green and brownish areas are pretty much oil. With that in mind, we have a number of productive horizons. These are formations that have produced oil and gas over the years. And they go from the most shallow formations of coal bed methane down to the very deepest in the Trempealeau dolomite. On this picture that you're looking at, the formations that are labeled in red are what we call source rocks for oil and gas. These are organic rich shales, which over time, those shales, the organic material in those shales matures into natural gas and oil. And then they migrate out of those formations and into the formations above and below. So things like the coal bed methane, that would be excluded, but the Berea sandstone, the Big Lime, the Clinton sandstone, Trenton limestone, the Beekmantown, the Rose Run, and the Trempealeau, these are all reservoir rocks that have been enriched in petroleum from the source rocks, the Utica Shale, the Marcellus, and some of the shales within the Ohio Chagrin Shale section. With that in mind, you have to be aware of the fact that natural gas is a part of our landscape. There's a lot of concern about natural gas in groundwater. It was there before we came here. It's still there now. That's not to say the oil and gas industry doesn't impact that. It can, but it is a natural part of our landscape. Back in June, I was lucky enough to be able to go out to one of Chesapeake's drilling sites and see firsthand how the operations go. And compared to earlier sites, like with the Clinton sandstone, things like that, I was very impressed with how the approach to oil and gas drilling is done in the shale gas. This is definitely a corporate approach, and it's one that really looks out for, in my opinion, the environmental issues. A lot of people talk about the Utica Shale. Very few people have actually seen it. Where we stand right here, it's about 7,000 feet below the surface. If you actually wanted to see an exposure of it, you'd have to head over to Utica, New York, southern Quebec. You can see it outcropping there. But we have a special treat for you today. If you were to head over to the YSU table, we've got some of the core samples from the Ohio Department of Natural Resources laid out. This particular core you see on the slide is from the Fred Barth well, and it's pretty much drilled. The core was extracted pretty much in the heart of what is speculated to be the oil-rich zone. As you move to the west, you get out of the mature zones, or where oil and gas has been generated, and out here in Wyandotte County, we've got another core on display, And this is a Smalley well from Wyandotte. And it looks a little different than the core from the last well, the Fred Barth well. It's lighter in color. The hydrocarbons have not been matured inside of it through heat processes. There's a lot of concern about hydraulic fracturing. And there's an awful lot of misinformation about hydraulic fracturing. A lot of information to the point of a lot of people really aren't even sure what it is. And so I want to straighten out a few of these things right here. What is hydraulic fracturing? First and foremost, it's a well completion process. It's not a drilling process. It's a way in which you complete a well so that you can extract natural gas from otherwise what we call tight formations. It was developed in the late 1940s. It basically uses water as a medium to induce hydraulic pressure on the formation, and it creates fractures in the rock, which allows natural gas, oil, other liquids to flow out of that rock, which otherwise would not be productive. It obviously improves the production of the oil and gas. It's been successful on more than 1 million wells in the United States and more than 85,000 wells right here in Ohio, and most of those are concentrated in eastern Ohio, right around where we are right now. Some of the basics on hydraulic fracturing. With the shale gas development, it's been combined with horizontal drilling technology. And what that enables us to do is, rather than just drilling through a formation that might be 150 feet thick and having access to 150 feet of that rock, you can turn the wellbore horizontal and drill out through the length of the formation as much as 5,000, 6,000, 7,000 feet. And that way you increase the surface area from what you can produce. Once you've drilled out the formation, you run protective casing, production casing. You cement that casing back. After the cement is set up, you run a perforating gun. It perforates through that steel casing, through the cement, and into the rock formation. Once that's complete, you pull the perforating gun out, and then in stages, you go in and you perforate, or you go in and you hydraulically fracture the formation using large volumes of water, large quantities of sand, and certain chemical additives that affect the way the hydraulic fracturing fluid works. What's a frac job look like? Here's a site from the Marcellus up in northeastern Pennsylvania. And what you can see from this site is it's large. Covers a good amount of area. This particular site that you're seeing here is a little bit smaller than others. It might only be 2 to 3 acres in size. And the reason why it's smaller, it doesn't require a frac water containment pond. If you look down in the lower right-hand part of the picture, you might be able to see a little pipe coming up out of the woods. That's actually the water supply source for the hydraulic fracturing that's going on in the picture. You can also see that the hydraulic fracturing operations is fairly complex. It requires a lot of different technologies, a lot of different personnel, a lot of different vehicles, different equipment. They're labeled on here so you can look at them. But overall, it's a pretty high-tech type operation. Here's another site. This site did not have a containment pond nearby, and so it could not supply water via a pipeline. Instead, the water comes by way of frac trucks. And if you try to count the trucks in there, I think you'll get up to about 100 and start losing count of them. Because of the enormous quantities of water, you need a lot of trucks to haul this water in. To talk a little bit about the geology, and I'll come back to the hydraulic fracturing in a minute. What you have here is a generalized section that shows the relationship of the Utica formation to the other formations that overlie it. A well penetrates vertically, and about 500 feet above the target formation, the Utica in this case, it starts kicking out, gradually working its way to a 90-degree angle. In order to do this, you change your drilling technology from rotary to mud motor. And you can gradually change the angle of the hole, half a degree at a time, until you get out to horizontal, and then you continue drilling with that mud motor down the center of the formation. If you think about it, it's a lot like threading a needle, not that easily done. And so you're looking at, again, pretty high-tech type stuff. The other thing I want to point out in this picture is that the separation of the target formation, the Utica, from the surface, the groundwater, the surface waters, is immense. In our area right here, you're looking at about 7,000 to 8,000 feet. And that rock that separates the Utica from the surface is largely impermeable. And one zone in particular, the saline salt, which is anywhere from 50 to a couple hundred feet thick, is totally impermeable. I'll come back to this in a moment, but one of the things I'm getting at is when you hydraulically fracture, there is no physical way that fractures can extend to the surface and bring frac fluids up to contaminate our groundwater. An important part of the process is how the well is drilled and completed. All oil wells require multiple, what we call strings of casing. It starts with a conductor casing that's basically drilled to stabilize the well so they can continue drilling. Conductor casing that's used on Utica wells is 20 inches in diameter, and it'll extend to whatever depth it needs to, generally down to firm bedrock. Once they set that casing, they put a shoe on it, and they pump cement up around the outside of the casing between it and the well bore to seal that off. The next thing they do is they go in with a smaller bit, about a 13.5-inch bit, and they'll drill down at least 50 feet below the deepest aquifer or freshwater producing zone, groundwater. They'll do the same thing. They'll run the casing, they'll run a casing shoe and pump cement all the way up to the surface, let that cement set. The next thing they do, they go in with a smaller bit. They drill out that cement, about a 9.5-inch bit, and they continue to drill down all the way to the formation target. If they encounter different or abnormal formation pressures, they'll run what's called an intermediate string to seal off those formations. They'll cement it back. The cement typically does not go up to the surface. The final string or drill, they'll do with even a smaller diameter. They go in, drill out that cement, go down, kick out, do the horizontal, drill the entire length of the formation, and then they'll set the production casing. That casing goes all the way from the surface to the very end of the hole. Typically, this is 12 or 13,000 feet in length. They cement it back well above the top of the formation and let that cement set. One of the points to be made here is that the shallow horizons, your groundwater and your surface water, are protected behind 3 and likely 4 different layers of casing, and up near the surface, 2 layers of cement. How does the process work? I've got a couple slides here that maybe you've seen on National Geographic's website. They're really nice graphics, but you go in and you drill. In the second picture, the production casing is being run into the hole. Once the production casing's in place, you come and you pump cement. That cement runs between the casing and the actual annulus, or what we call the wellbore. And once that is all set, you then run a perforating gun. And the perforating gun, these are pretty interesting. They're also dangerous objects, but it's a gun that comes in different sections. It's a tool, cylindrical, and it's got 1.5-inch size bullets, at least the ones I've looked at have. And those bullets have a charge behind them. And that charge will actually puncture an 1.5-inch diameter hole through the steel casing, through the cement, and fairly deep into the formation. And what that does is it provides an avenue for the fracturing fluids to get into the formation. So, and obviously I've shown that in the next picture here, but then once you have these holes perforated into the formation, you then start the hydraulic fracturing process. This is done in stages. It's not the whole length of the horizontal. The wells that were recently reported on down in Carroll and Harrison County by Chesapeake Energy, they were doing these in 14, 17, 24 stages. And it takes a fair amount of time. So it might be only 250 to 300 feet of the actual well bore is hydraulically fractured at each time. And this will be spread out over, depending on the length of the well bore, over a period of anywhere from 7 days to 20 days. And drilling's a complicated thing. You run into various problems that can also delay it. So once we've got the fracturing done, then through a production string, you can allow the fluids to come up to the surface. And at the surface, then they are separated out, put into pipelines. The flowback fluid, for the most part these days, is being recycled. There's a tremendous economic incentive to do that. That which can't be recycled will go along with brine water. And a lot of that's coming to Ohio and being put into Class 2 injection wells. We'll come to that in a little bit. There's a tremendous interest with the industry to know just where these fractures are occurring when they do hydraulic fracturing. The reason for it is obvious. If you fracture beyond the target formation, you won't be extracting the fluids out of the formation you want. You'll probably be extracting brine, high concentrated salt water out of the formations and above and below, in this case the Utica. That's nothing you want to do because it can render the well uneconomic and it's a big waste of money and effort. One of the ways that this is monitored is by doing what's called microseismic monitoring, where in an adjacent well you lower geophones and you can actually record microseismic events that are occurring as the shale is being fractured. And you can actually map and plot how far those fractures are extending into the formation. Keep in mind, it's very important to the producing companies that these fractures are done correctly. If they're done incorrectly, it can render the well useless or uneconomic. Here's what a perforating gun looks like. In your upper right are some guns laying on the rack. The little holes that you see in them, those are the actual bullets. Over on your left, you can actually see the bullets, what they look like before they load them into the gun. And then down on your lower left is a computer animation picture that kind of shows how these things are fired off and go through the layers of steel casing, cement, and into the rock. There's a lot of information that's available, factual type information that you can get from the Department of Natural Resources, either through the Geology Division or the Division of Mineral Resources Management. This particular information here comes from the Geology Division. They have an interactive map where you can go and look up any well you want. You can click on the well and bring up all the information about its completion. What I've done here is taken the Niter 3H well that Chesapeake drilled earlier in this year and reported some of the peak production rates on back in September, and give you the basic information on this well. This is all publicly available information. That's how I got it. I've just put it in a different format here. It was a Utica completion. The horizontal leg of the well was 4,152 feet in length. It was a 14-stage fracking completion. It took 7 days to do the frack job on it. Each frack stage, approximately 250 feet long, had 60 different perforations produced by the perforating gun. The amount of water used in this well was almost 6 million gallons of water. It's a lot of water. What often goes unnoticed is the amount of sand that's used in producing these wells. In this case, over 3,000 tons of sand was mixed with the water and the chemicals as part of the hydraulic fracturing. So a lot of sand goes into these as well. The peak production, as reported, was the equivalent of 1,615 barrels of oil per day. Those kind of numbers are what we usually think of Texas, Oklahoma, Louisiana. These are not the kind of numbers you think of coming from Ohio. And so the potential economic benefits to Ohio, job creation and things like that, if you want to look at a number that kind of testifies to that, look at these production numbers. Very, very impressive stuff. As far as the casing record on this well, which again is public information, anybody can look it up. Conductor casing is a 20-inch casing, run to 80 feet. The surface casing, which protects the shallow water, the groundwater aquifers, was run to 466 feet. Is a 13 3/8 inch diameter. The intermediate casing on this well was run to 1,728 feet. All these casing strings go from the surface to the depth. So if you look down on top of the well, it's kind of looking like a series of concentric circles. The final production string was run all the way out to the end of the wellbore at 12,503 feet, and it was a 5.5 inch diameter casing. And you can see why V&M Star is very interested in producing this casing. 12,503 feet of casing used on one of these strings alone. Think about it, that's about 2.5 miles of pipe. A lot of concern is out there about the ingredients of frack water, or frack solution. Here are some of the major or basic ingredients that are needed for it to work. Obviously, water is the biggest component, makes up about 98 to 99.5% of the frack solution. The purpose of the water is to provide a medium for applying the pressure to the formation, and it carries the sand. We'll get to the sand next. The sand is called a proppant. What that sand does is once the formation is fractured, the sand flows in with the hydraulic fracturing fluid and it fills the fractures. Think about it. You have to fill the fractures with sand because as soon as you release the pressure, if you don't have sand to fill up the fractures and give it permeability, the fractures will close right back up. And that's why you use such large amounts of sand. Acids are commonly used. Hydrochloric acid is a common one. A lot of minerals have calcium carbonate in them. It reacts with acid, it dissolves it, it breaks it down. It helps the fracking process. A number of different things are used. A cross-linker. It helps maintain fluid viscosity. Water by itself is not going to transport a whole lot of sand. It needs to be thickened so it can support the sand. Cross-linkers do that. Other things like gelling agents help do that. It makes the stuff into a gel-type material. Iron control. Iron's always a problem. It plates out on things, it scales, it prevents fluid flow. Clay stabilizers. Clays tend to react with water. By putting stabilizers in them, it keeps those clays from swelling up and closing up the fractures. Breakers are added. What the breakers do is after the fracking is done, it allows the gel to break down into more of a liquid so it can flow back out of the well. And then another additive are antibacterials. Living way down inside the earth are lots of bacteria. There's bacteria that produce this oil in the first place. You got to control the bacteria because they will create different corrosive type byproducts that will harm the well. If we take a look at the Marcellus, which is quite often used when we look at the Utica because we're in the early stages of exploration of the Utica. If you take a look at the Marcellus, you can get a pretty good idea how the Utica exploration and development may move forward. You look at Marcellus frack water, the typical Marcellus frack water is made of 80% fresh water, about 14% recycled water, 5% sand, and then less than 1% is other, which are the chemicals you add to it. The chemicals we just talked about are shown over on the circle on your right, and all the things we just talked about are shown in the various percentages as they're found. There's a lot of concern about being able to access what these different hydraulic fracturing fluid additives are. There's 3 different places I'm aware of where you can get this information. For Pennsylvania, you can go to the Pennsylvania Department of Environmental Protection, where this is a snapshot taken from one of their websites that shows the different components, its concentrations, exactly what it is. You can also go to the Ohio Department of Natural Resources Mineral Resource Management website, where they have MSDS sheets, material safety data sheets, that talk about each of the components, health risks associated with it. MSDS sheets are not easy to put up on a PowerPoint presentation because for each chemical you have multiple pages of information. Another organization that has popped up in the last half year is Frack Focus. It's a national-based organization that will post the components of hydraulic fracturing fluid out on the web, not just for the Utica or the Marcellus, but all the other shale gas producing formations across North America. Some of the truths about hydraulic fracturing. It uses large volumes of water. To me, this is one of the biggest concerns. Between 4 million and 22 million gallons of water per well. It's a lot of water. It uses chemical additives. Generally, between 0.5% and 2% of the frac fluid are chemical additives. Some of them are benign, some of them are toxic. You got to be aware of these. Large quantities of sand. I don't think sand is a problem in Ohio. The glaciers gave us a tremendous wealth of sand. Other parts of the country, sand is expensive to transport and truck in, and so it's a limiting factor in some areas. It won't be a factor here in Ohio. Another truth about hydraulic fracturing is that negligent handling of fluids is dangerous. I'll get into this more in just a moment. And then recycling of these fluids and proper disposal is also very important. Some of the myths about hydraulic fracturing. Induced fractures extend to the surface. That's a myth. It's physically impossible. I could run off probably 5 basic reasons why it can't happen. Probably the most primary reason for it is the pressure gradient is towards the wellbore. Any fluids that are going to be moving into that formation are going to be moving right back towards the wellbore. That's where the pressure is drawing it to, not towards the surface. Another obvious fact here is that as fractures work their way up through the formation, you're looking at horizontally layered sedimentary rocks. Once they hit bedding planes, those fractures are going to go horizontal. They're not going to go vertical. A number of other reasons as well. Chemical additives are a secret. Most of them are not. Some of them are trade secrets. And they are trade secrets, or they're confidential to the companies, because this is a highly competitive business. If you give out all the information on your components you use, you give a leg up on the competition, and it undercuts your business. One of the biggest myths of hydraulic fracturing is it causes tap water to ignite. The only thing that causes tap water to ignite is methane in your water and putting a match to your water. Believe it or not, methane is a common part of our groundwater. It may not be in high enough concentrations to ignite. In many places it is. In large part in this area because of the coal that we have very close to the surface. Everybody knows about canary in the coal mine. It's there to detect methane as a protective measure for the miners. Coal is full of methane, and it's very close to the surface. One thing that is true about drilling is it vibrates the earth. And natural gas that's distributed through the rock formations near the surface, within the aquifers, it can cause that natural gas to migrate and accumulate in higher concentrations than prior to the drilling. That is true, but it has nothing to do with hydraulic fracturing. Another recent one is that hydraulic fracturing triggers earthquakes. Not true. There's a remote possibility that it could, none such on record. It does create microseismic events. You'd never be able to detect them at the surface. The most sensitive of seismographs cannot detect these. You can only detect them in boreholes that are drilled adjacent to where the drilling's going on. The other one, and this goes without saying, fracking is not a drilling process. As a geologist who spent 15 years in the oil business and 20 years as an environmental scientist, fracking is not a drilling process, it is a completion process. Hopefully that'll get straightened out someday, but I know it's a popular phrase and it carries some weight with it. And the other myth is frac fluids migrate to the surface. They don't. Let's move on to Class 2 injection wells, because this is something that everybody in Ohio should be concerned about. Ohio is different from Pennsylvania in that the Ohio Department of Natural Resources has primacy over Class 2 injection. Class 2 injection is the best management practice for disposing of production fluids that come with the oil and gas industry. Ohio's had primacy, which means it separates us from the federal EPA. The reason why we have primacy is our practices meet or exceed the standards of the federal EPA. As a result of having this primacy and a rich history in oil and gas development, Ohio has, count was yesterday, 192 Class 2 injection wells. Not all of them are shown on this map because it's a little bit dated. I think there's 160 or so shown on this map. But you can see that most of them are concentrated in eastern Ohio. There's an obvious reason for that. That's where the oil and gas production takes place. This is how we get rid of brine fluids and frack flowback waters. It's generally the best management practice because it puts the stuff back in the earth where it came from, and these are toxic materials. You don't really want them up at the surface. So it's a good way to get rid of them. The unfortunate thing about Pennsylvania not having primacy over their injection is that they only have a handful of injection wells, and they can't handle the capacity of all the flowback and brine that's produced with the Marcellus production. And interstate commerce laws prevent Ohio from saying no to these frac fluids coming in from Pennsylvania and West Virginia, so they're coming to Ohio's Class 2 injection wells, and they're putting a pretty good tax on these wells. And so we're putting a lot more fluids into these wells than we have in the past. We're adding more wells to accommodate this, but overall, I'm not really fond of the practice. I'd like to see it just limited to Ohio wells, or at least jack up the injection fee to the point where it becomes undesirable to the other states to bring it here. Something that's been in the news quite a bit, and I've been pretty heavily involved with, is the seismic activity that's coincident with the North Star number 10 injection well over on Salt Springs Road. I'm sure some of you have heard about this or heard about the earthquakes. I spent 5, 6 years of my formative years living in Southern California and experienced a number of major earthquakes. And I know that coming to Ohio, people aren't used to earthquakes, so if you hear about one on the news, you think it is a terrible thing. It's not a good thing, but it's not a terrible thing either. Probably very few people in here even felt those earthquakes. The number of felt reports that go into the Ohio Seismic Network is around 2 or 3 per earthquake. But the fact of the matter is we've had 8 earthquakes in the past 8 months. And coincidentally, these earthquakes started occurring about 5 months after injection started on the North Star number 10 well over on Salt Springs Road. The map you're looking at here shows the distribution of those earthquakes. This particular well was drilled all the way down to the Precambrian basement rocks. And in the driller's report, and from talking from people at the Division of Mineral Resource Management and the Geology Division at the ODNR, that granite basement rock was fractured. Fracturing in granite often means that there is a fault. Doesn't mean there is one, but it can mean there is a fault. Having this well completed into these basement rocks probably wasn't a real good idea. It is possible that injection of the fluids may be triggering earthquakes, but until we can place seismic monitoring stations in the vicinity where these earthquakes are occurring, we can't tell for sure the depth from which these quakes are coming. This particular well is over 9,000 feet deep. If it turns out, if we set up a seismic monitoring network and it turns out that the earthquakes are coming from that depth, I think that's pretty much obvious, not proof, but awfully strong evidence that it's leading to this injection is causing these earthquakes. Keep in mind, we got 192 injection wells in Ohio. One of them is producing earthquakes. So it doesn't mean that all injection's bad, but we got to be keeping a careful eye on this particular well. There's another well that's permitted, I don't think drilling has started, that is fairly close to this particular location. And I've been told that once that well's completed, this well is going to be shut down and the new well will take on that actual injection process. And it won't be completed down to the basement. I meant to forward to this slide here, but over on your right is a standard diagram of what an injection well looks like. It's basically like an oil well. It's got multiple strings of casing to protect the surface, groundwater, the other formations. It's perforated. The injection fluids go out through those perforations. You're basically doing the opposite of producing oil. Instead of oil and gas coming through those perforations, brine water and flowback water is going in through those perforations. Over on the left, nobody's going to be able to read it unless you're right up front here. This is the actual well summary. It gives you all the information on this particular well. I encourage everybody to go out, if you're interested in this, to go out onto the ODNR geology website, pull up the interactive map, go and take a look at this well or any other well you want, and you can get all the information you desire. As far as earthquakes in Ohio, nothing new. We've had them for a very, very long time. Most of them are rather small. The ones that were occurring here in Youngstown were between 2.1 and 2.6 on the Richter scale. We're able to locate the surface fairly accurately using seismometers like the Ohio Seismic Network. We have one of those at Youngstown State University. Myself, along with one of my students, Chris Grope, operates this station and has led to the information that's allowed us to locate these earthquakes. But if you look at the state of Ohio map, you'll see there's a broad distribution of these quakes, and they've occurred over a long period of time. These earthquakes are associated with the basement rocks, the granites and the gneisses, igneous and metamorphic rocks that were created over 1 billion years ago. Weaknesses in those rocks occasionally cause a little bit of movement. If you inject fluids into those fault planes in those rocks, it can increase the pore water pressure, reduce the friction, and cause some movement. We've got to be watchful of this. These basic faults that I've talked about, they're deep basement structures. This is a map here put out by the Department of Natural Resources. It shows a lot of these structures. A lot more of them are going to be defined as more and more oil and gas development goes on with the Utica, more and more seismic surveys are done, and we'll be able to define where these faults are better. But at this point in time, our knowledge of these faults is not all that great. You can't just stand at the surface and pick them. You either have to use seismic evidence, drilling evidence, earthquake evidence to locate them. And finally, I want to bring attention to the environmental awareness or activism that surrounds the Utica play. This is a very important aspect of development of oil and gas in Ohio. The reason why it's important is environmental groups keep the oil industry on their toes. Oil industry knows that if they make a mistake, it'll be, with modern technology, communication technology, it'll be a matter of minutes, if not hours, before that information is distributed to the public. It's out in the media. And the last thing the oil industry wants to see happen right now is have the public opinion turn against them. Right now, with the economic development, the jobs, the cash flow that may be coming to Ohio as all this unfolds, the last thing we should want to have happen is have this stall out, because I've lived in Ohio almost all my life, Eastern Ohio. It's been economically depressed for most of my life, and I'd like to see people that have been unemployed, underemployed, have job opportunities, and get back to work and make this state what it once was. And the environmental groups play a very important role in making sure this happens as we move forward, because mistakes can't be tolerated. I certainly won't tolerate them. I hope you won't either. And with that, I'd like to thank you.